Hey guys, today we're going to be looking at energy, specifically energy from nuclear reactions. So in today's video, you should be able to calculate the mass and energy changes for nuclear reactions and calculate the binding energies for a nuclei. The energy in a nuclear equation or reaction is due to what's called mass defect. So when we transfer from one nucleus to another, there's always going to be a difference in the mass itself between the products and the reactant. It's going to be very, very small, but it's enough to cause a large amount of energy to be released. We look at that mass defect with the following equation, E equals mc squared. And the mass right there is our change in mass, our mass defect that we are looking at. So using this equation, we can find out how much energy is released during a nuclear equation if we know what the mass defect is. For instance, if we have uranium-238 and it goes to thorium-234, and it also releases an alpha particle. In this process, the difference in the masses between the products versus the reactants is negative 0.0046 grams. Not a very large amount. That's a very, very small amount, as a matter of fact. But it's enough to cause a large amount of energy. So if we have 1 mole of uranium, we get a mass defect of negative 0.0046 grams. So let's see what happens to that. We're going to take that and put that into our equation right here. And we want to put it in as kilograms because of the unit of joules. So joules itself is equal to kilograms times by meters squared over seconds squared. So we want to have our mass in kilograms. So to put this from grams into kilograms, this gives us negative 0.000046 kilograms. So that is our mass defect. And then C is our speed of light, 3.00 times 10 to the 8 meters over seconds, and this is squared. When we solve for our energy, we get a value of negative 4.1 times 10 to the 11 joules for 1 mole of uranium. That is a large amount of energy. When we start looking at chemical reactions, you'll see how different in energy these are. But this is like I said, a tremendous amount of energy. And it's negative because heat is released during this. So we can then convert this into MeV, which is mega electron volts, which is a common binding energy unit. So we would say that 1 joule is equal to 6.242 times 10 to the 12 MeV, where again, MeV is mega volts. Okay. So that can then be converted into mega electron volts, which is a unit that is fairly usable when discussing binding energies. So where does this energy come from? It comes from the difference in energy between our individual parts of our nucleus versus the mass of our nuclei itself. So the individual nucleons have a greater mass than the combined nucleus. So when we combine all the parts, you're going to have a different mass than if they are all individual. This difference is that mass defect. Okay, And we could actually solve through this. We could go through and solve for our number of protons, number of neutrons, and then compare it to our mass of our nuclei. And the thing that's holding everything together is called the nuclear binding energy. So it's what's holding the individual nuclei together. And it comes from that mass defect. So essentially, part of the masses of the nucleon are being converted into energy, and that energy is that nuclear binding energy. In order to determine what type of nuclei are going to undergo nuclear processes, it's helpful to look at our nuclear binding energy per nucleon, which is what we see in this table right here. So you're basically taking your binding energy and dividing it by the number of nucleon that you have, and that gives you information about how best to access nuclear energy. So for instance, if we have heavy nuclei, if we split that apart, we're going to gain stability, and that's going to give off energy during that. So by splitting, the nuclei gain stability, and that gives off energy. It's more energetically stable, it's much happier. This process of splitting the nuclei is called fission. Okay? And then if we have really light nuclei, we can take them and we can combine them, and that's going to emit a large amount of energy as well because they have a very low binding energy per nucleon. Adding them together, again, makes it more stable, and that releases a large amount of energy. So our lighter nuclei are going to emit a great amount of energy by combining. Again, because we're getting to a more stable, greater binding energy per nucleon value. This is called fusion. So we're fusing things together. So very low mass number nuclei are going to combine in a fusion reaction, and that releases energy. Very large mass number nuclei are going to split, producing smaller nuclei that are more stable, and that also releases energy in a fission process. Okay, let's try an example. We have helium-4, which can be produced by the nuclear fusion of lithium-6 with deuterium. So let's try this out. We're just going to go ahead and write what we know. So we have lithium-6, and it's reacting with deuterium. Deuterium is hydrogen with an extra Deuterium is hydrogen with an extra neutron, so it's going to have a mass number of 2, and it looks like that. So when those combine, they produce helium. Now, looking at this, hopefully we notice that they do not match up on both sides. We have 8 as our mass number on the left side, 4 on the right, 4 as our atomic number on the left side, 2 on our right. So we need 2 helium nuclei to balance this out. Now, the first thing we want to do in any fusion, fission, bending energy equation reaction, we want to determine what our mass defect is. So our mass defect is going to be our products minus our reactants. So each helium nucleus has a mass of 4.00260 AMU. So we're going to multiply that by 2 because we have 2 helium nuclei. So 2 times by 4.00260 AMU. And we're going to subtract the masses of the two reactants, our lithium at 6.01512 AMU, and our deuterium at 2.01410 AMU. And what we get is a mass defect of negative 0.02402 AMU with correct sig figs. And then we're going to want to put this into kilograms so that we can put it into our E equals mc squared equation. And to do that, we're going to convert from AMU to kilograms with the following conversion. So 1 AMU has 1.6605 times 10 to the negative 27 kilograms. We do that calculation, we get a mass defect of negative 3.989 times 10 to the negative 25 kilograms. That can go into our equation, E equals mc squared. And we're going to multiply that by our speed of light. Squared, and we get an energy of negative 3.585 times 10 to the negative 8 joules, so it will be a release of energy. And I just want to point out that this is for one fusion process, so one atom of lithium fusing with one atom of deuterium. So this is not a lot. Okay, so I'm going to bring that up again in just a minute, but the first thing we want to do is we want to convert this into mega electron volts. So use the conversion we were given earlier, 2.242 times 10 to the 12 MeV per 1 joule. And this gives us a nuclear binding energy. And this gives us an energy of 2.238 and this gives us an energy of negative 2.238 times 10 to the 5 MeV for this process. We can also take this value right here, which is currently for one atom, and figure out how much it would be for a whole mole of atoms. So the other way you could write this is negative 3.585 times 10 to the negative 8 joules per atom. And then using Avogadro's, 6.022 times 10 to the 23rd atoms, we can convert it into moles. And when we do that, we get a much more impressive number of negative 2.159 times 10 to the 16 joules per mole. So that's how many joules of energy are released by this fusion process. And that's a lot. So, okay. That is everything I have for you guys today. I will talk to you guys in the next one.